In the last lecture, we looked at how to model noise with an amplifier using a perfect noiseless amplifier and surrounding it by components that were emulating the noise voltages and noise currents associated with that amplifier. In this lecture, we'll look a little more about amplifier noise performance and the benefits of matching the source impedance for a given amplifier. So looking at the circuit we have here, we've got a source resistance here, and in this instance it's feeding an amplifier set up as a gain of ×1, but it could be much higher than that. And what we have here is we have a line drawn that's equivalent to resistance, and a resistor only, and also the performance of the amplifier plus the resistor. So we can check this quite simply to see if it's correct, and we find that a 1 k ohm resistor here gives us about 4 nanovolts per root hertz, which we know from previous calculations is exactly right, because a 1 k ohm resistor generates a noise power spectral density of about 4 nanovolts per root hertz. And similarly, if we move up to 100k, we discover that it measures 40 nanovolts per root hertz. And if we continue from 100k up to 10 megohms, we discover that it crosses at 400 nanovolts per root hertz. For every 2 decades of increase in source resistance, you increase the noise spectral density by 1 decade because it operates as the square root. The blue line here defines the thermal resistance associated with RS, the source resistance. And the grey line shows the performance of the OPA27 bipolar op-amp connected to the resistance. We can also draw on this graph the VN figure that's stated in the datasheet, and in the example here it's about, and we can also draw here the noise current associated with the amplifier multiplied by the source resistance. If the noise current is a constant, then as the source resistance increases, so the noise current increases up and down this line here. Looking at a slightly different amplifier, looking at the OPA277, here we have the similar calculation. We have the fundamental noise voltage associated with the amplifier. We have the noise current from the datasheet and the amplifier multiplied by the source resistance. And we also have the V-Thevenin value here, which is the resistive power spectral density from the source resistance itself. And again, checking very quickly, 1 k ohm is approximately 4 nanovolts per root hertz, which is a good check just to make sure that we're in the right ballpark. It is impossible for any amplifier to reduce the noise coming from your source. All amplifiers add noise to the through the raw basic thermal noise of the source. And the goodness of an amplifier is it depends how small a noise increase it adds to the source. And we have this concept called noise figure. And we define the noise figure as the total equivalent input noise divided by the Boltzmann noise or the thermal noise of the source itself. And we usually express noise figure in decibels, and the noise figure is 20 log the total input referred noise divided by the source resistance noise. And bearing in mind that the total input noise also includes the noise from the source resistance, this figure must always be greater than 1. The noise figure and the noise performance of an amplifier depends on the amplifier choice and also the source resistance. There is no best amplifier for low noise. It depends what it's going to be used for. If we look at some typical amplifiers, I've identified 4 fairly good amplifiers here, and we can look at the noise voltage and the noise current. And in each of these amplifiers, they have been optimized for different particular source resistances to get the optimum noise performance. So in the first one, dividing the noise voltage, which is 1 nanovolt per root hertz, divided by the noise current, we land up with an optimum source resistance here of 446. That amplifier has a bipolar input stage, and so the noise current is relatively high. Whereas if we look at perhaps the OPA 827, it has a much lower noise current. It also has a higher noise voltage, so its optimum input resistance, source resistance, would be 1.82 megohms. So it's important to understand and examine what the source resistance is on your application before you choose your amplifier. We can also plot this graphically on a scale. And what we've done here is we've taken the different amplifiers that we looked in the previous point, and we plotted the noise voltage and the noise current performance across a increasing source resistance, going from a very low 1 ohm on the left hand side all the way up to 1 gig ohm on the right hand side up here. And here we can see that each amplifier is an ideal match for a different source resistance. So for a low source resistance, you would want to use the AD8597, whereas if you're looking for a very high source resistance, perhaps 10 megohms, you may want to use the OPA 827 because it has a very high optimum resistance. Now let's look a little more about noise current in association with amplifiers. So this circuit here looks very similar to the analysis you would do for bias currents. But the key difference here is because the noise currents in both the plus and the minus connections to the amplifier are uncorrelated, you have to add them as a square. Each of these noise sources at this point here are completely random, so you have to take the square of them to calculate out the total noise current affecting the amplifier. So far we've really only talked about thermal noise and the effect of thermal noise on design parameters. Now let's move forward onto a different type of noise, and this is a type of noise called shot noise. Shot noise depends when electrons cross a potential barrier. So they cross a junction, or they operate within a FET, or they operate within a thermodynamic valve. And shot noise is caused because charge has a quantity, and the emission is uncorrelated. So while you may have a general flow of current through a junction, the actual arrival of each of the electron charges is fairly random because it's uncorrelated. So here we have on the left hand side the effect of an uncorrelated arrival of electron charge. Going from the blue area at the top to the red area at the bottom, the electrons will arrive at random times. Whereas if they're crossing a resistance, then we land up with correlated charges because we have the current flow going in and the current flow coming out happens at pretty much exactly the same time. So one electron in, one electron out. So it's correlated. Good examples of shot noise happen with things like photodiodes. It can happen on bias currents of transistors or base currents in transistors. And also it's the effect of noise across a diode. Shot noise, similar to thermal noise, works out the current, and it's the square root of the electron charge times the DC current source times the bandwidth. And it only occurs when current is flowing. So shot noise in an amplifier can only occur when the amplifier is actually switched on and operating. Shot noise increases with current, as you can see from the equation up here, and it increases with the square root of current. And we can actually use that to our benefit. So if we define our signal to noise ratio as the value of the DC current divided by the value of the shot noise, we discover that as the DC current increases, we actually improve our signal to noise ratio from the due to shot noise, because although the shot noise is increasing in absolute terms, it only increases by the square root of the DC current, whereas the DC current increases linearly as it's increasing. So you can improve the performance of your amplifier by running them with higher currents. And that's one of the techniques you would use at the design of the input stage of an amplifier. We've now looked at the effect of thermal noise in amplifiers, and we've also looked at the effect of shot noise in amplifiers. In the next lecture, we'll look at the last and final type of noise, which is flicker noise. Thank you.